like that, doesn't it, Stan?
No. The trouble with doing a stin gun method in this is the fact that we're dealing in three-dimensional space, so it'd be a lot more difficult to go, all right, so the magnetic field's going in that direction. And,
So it's probably just better just to memorize IJK.
yeah.
That's your paper.
All right, the second one, an object's traveling at 0.9224 times the speed of light. What's the Lorentz factor?
Relativity.
Now, these are plug and chug, so, I mean, if you're trying to figure out what's the Lorentz factor again, you go to the first page, you look, oh, there's the formula.
Sorry, would you mind repeating the speed?
0.9224, so V is, let's see. So 1 over square root of 1 minus 0.9224.
Oh. And that's a number, you got, let's do that real quick.
And it's something just magical.
.984.
I got the final Lorentz factor to be 2.589.
Oh, he did it all the way through. I was just doing the square for some reason.
Oh, okay. If you end up with a Lorentz factor less than 1, you made a mistake. Gamma, the smallest it can be is 1.
What is B?
Beta? Beta is just V divided by C. So if I just said, instead of saying V is 0.9224C, I could have just said he was traveling with beta equal to 0.9224. Saved a little ink. This ratio shows up so much that they got lazy / efficient by giving it another letter.
And C is speed of light.
Yes.
I have to disagree. They could have used one of those betas for one of the 6 use of knots.
You know, get in a position of power, you make the difference. The next question is related to show that one unit is equal to another unit. I don't think. Show that a kilogram per Tesla Coulomb is a unit of time.
Can we do it?
I believe in us. I think we can.
You hold a very high standard to us.
Kilogram Tesla Coulomb.
Just a second.
All right, so I need to bring seconds into it somewhere. I know that from this equation right here, that a Newton is a Coulomb meter per second Tesla. Well, I got Coulomb Tesla right there, so a Coulomb Tesla would be Newton second per meter.
Wait, how did we know that a Newton was equal to a Coulomb?
Meter Tesla per second? Because this formula we're claiming is correct. And so looking at the SI units, that would be a Newton, Coulomb, meter per second, Tesla.
Okay, that makes sense.
So we now have kilograms divided by that. So I have kilogram meter per Newton second. Well, I know a Newton is a kilogram meter per second squared. And so then we've got some canceling to do. Meter cancels, that second cancels one of those, kilogram cancels, and what we're left with is 1 over seconds, which is just seconds.
You really make
Just
it
a second?
Pardon?
That is weird to look at, 1 over a second.
Or I could have at this point done kilogram meters times the reciprocal of that, which is seconds squared per kilogram meter seconds. And get to the same place.
Yeah, but the first one makes more sense because of our reciprocal rule. When you got it in the denominator, it just flips, right?
Yep. So for evidence, this, my justification for this is F is equal to Q V cross V.
Which we know is.
And then my justification for, this, F equals MA.
Generally speaking. And then,
And those are the only two equations I needed.
yeah, a whole lot of force.
And I'm sure there's a dozen other ways of doing it.
Which
Some
is the
do that.
scariest part.
Some dude out there gets paid to do that.
Go down the wrong rabbit hole.
Oh, yeah.
You waste like 15 minutes. Like this. None of these working.
Yes, that is true. Yeah, the original, that was what showed up in a variation of, the original question was using as many different metric units as possible without using any traditional unit for time, create an equivalent unit of time. So that was also show that it is an equivalent unit of time. So it would come up with as complex a way as possible.
Okay.
My friends don't think these are as cool as we do. I find that disappointing.
I think you need new friends.
I do too. I mean, I thought they would think it was cool. What are you guys suck. You don't think this is cool?
I mean, I think it's pretty.
A kilogram per Tesla coulombs equal to a second? No, it's not. Here, yeah, it is.
Well,
Well, that's your chance to go, who raised you?
even better, who hurt you?
Were you raised by wolves? I don't even know this basic, man.
All right, now we get into a slightly more interesting question, I think. You have two concentric arcs of wire connected to a complete circuit. There's a drawing for this one. So I've got those are semicircles.
Rainbow.
Current is flowing this way. I have some point P right there, smack dab in the middle. R2. I appreciate, I imagine more than one person thought D2, but no one said it, so thank you.
I thought it.
R2 is bigger than R1. The length of the outer arc is L. And current is, as noted there, what is the magnetic field? Magnetic field at the common center. In other words, at point P, what's the magnetic field?
Wow.
All right, so we basically got four segments here. We've got, we'll call it 1, 2, 3, and 4. All going to be contributing here. There are shortcuts and complex ways of doing it. Let's hopefully do, at least set it up, and then we'll talk about which method to pick. So the magnetic field at P is going to be the magnetic field from at P from 1 plus the magnetic field at P from 2 plus the magnetic field at P from 3 plus the magnetic field at P from 4.
Okay.
So again, 4 segments. I've got, I'm just going to do each one independently and add them up.
That makes sense.
So then it comes down to what is the magnetic field from a current. The hard way is to use the Biot-Savart law. However, we have a simpler way. If I have a loop of current here, the magnetic field in the center is mu naught I over 2R. We derived that in class, there's a video of it as well.
Unite.
But if you recognize this is, well, I know for a full circle, we've got a shortcut formula for it. And since this is a semicircle, it's gonna be half that.
Just regular R?
Yeah, it'd be 4R.
Oh, half that.
So BP, one is gonna be mu naught I over 4R1. Now we have to worry about direction. What is the direction of the magnetic field at P because of this first segment here?
Out of the page.
So it goes into the, right,
Yeah. That page.
out of the page.
So if we go with I, J, K, so that'd be K hat. And then 3 would be the other direction, so negative mu naught I over 4R2.
Oh, because we got negative K. Oh, okay.
It's gonna be in the opposite direction.
Will that formula be on the,
This is probably gonna, the formula page is gonna look something like that.
So where did that first one come from?
Where
The BP one?
where did that come from?
Yeah.
It's the magnetic field at the center of this semicircle.
Okay. So how did we get 4R from 2R?
A full circle is this, a half circle would be half of that.
Oh, right, okay.
Wait, so went I down out of the page?
Yeah, so at this point right here, current's flowing this way, so the magnetic field inside is out, and over here it's in. But it's, and then for the outer one, it's going like that, so it's going in at P and out here.
Do segments 2 and 4 cancel each other?
No.
Or add to each other?
Well, they would add, but
Like double of one, I guess.
R is a vector from the center to where the current is. So if that's R right there, DL is in the direction of the current flow, so that's DL. And so DL cross R, DL R. So DL cross R would be, get something backwards there? DL cross R. Oh. You know, I avoided that mistake when I did this in class. R is from the element creating the magnetic field to where you're issuing the magnetic field.
Okay, so towards P.
So DL cross R comes out. Here, if I take the segment here, DL is this way. R is that way. What is the cross product?
0.
Yeah. So they don't cancel each other out, but they don't
Oh.
contribute anything.
Wait. Great.
Oh, well, that
Oh.
makes sense.
Also, both 2 and 4 will cancel each other out. Both B.
2 and 4 are both zeros, so do they cancel each other out, or they just
Well,
don't exist?
their components cancel each other out. You know, the cross product cancels out.
Oh, okay.
Well, it's just because it's the direction they're going, they don't contribute anything to the electric field,
So
Magnetic
they're,
field.
magnetic field.
Yeah.
so theoretically, they're making a magnetic field, just not at point P.
Correct.
Okay.
Yeah, they're creating a magnetic field above and below. Actually, anywhere except along that line.
That makes sense.
And so the final, we get U naught I over 4R1 minus U naught I over 4R2,
Oh.
K hat. And
Well, oh, no, they won't cancel.
the magnitude would just be, the question asks for the magnitude, that's the magnitude right there. And if you really were inspired, U naught I over 4, 1 over R1 minus 1 over R2. It depends on what final form.
mu naught is a given value, right?
Yeah, the mu naught is 4 pi times 10 to the negative 7th
Yeah.
decimeters per ampere. That would be on the formula page.
I remember. It's on the formula page. No, but. So the difference is a Friend's problem in particular. It's just the radiuses.
Yeah.
That's pretty cool.
Okay. Yeah, I found it on the formula page.
All right. Add to the fun, a lithium nucleus, and I give the mass and the charge, is shot horizontally into a room filled with a magnetic field with a strength of 0.059 Tesla pointed vertically. How long will the nucleus be in the room before its path has turned 75 degrees? Assume the particle does not leave the room for the duration of this problem.
Is this being rotated?
All right, so
We got a room.
got a room, there's my room right there. Magnetic field coming up,
What view is this?
overhead view.
Noah's Ark colorized 1400.
And I got a lithium nucleus that's being shot horizontally. So I got a lithium nucleus going this way. And nucleus, so that is 3 plus. Charge is 4.8065 times 10 to the negative 19 coulombs. Mass, 1.165 times 10 to the negative 26 kilograms. And as it comes in, it's gonna start to turn. So let's make sure that we got this going the correct way. I got the going positive that way, magnetic field coming out, it will be forced down. And so, or forced in that direction. So it's coming in at 0 degrees here, and I want to know at what point is it 75 degrees. So that time.
This sounds like a calculus problem. Don't know why.
Let's find out. All right, so I have a positive charge coming into a uniform magnetic field. It's a circular motion, this is a centripetal motion problem. I know that the force is QVB, F equals MA. QVB, it's perpendicular. V and B are perpendicular, so it's just, the magnitude would just be QVB, is equal to mass times the acceleration, which is V squared over R, or omega squared R, depending upon which one makes more sense. I know that, which one does make more sense?
The angular one?
Probably guessing that one. Sorry, which one were you going for?
That one?
That one?
Yeah.
Okay. I know that it has some angular speed.
Alright, man.
Or saying the other one makes more sense.
It might be. Is equal to QVB over MR. I know Q, I don't know, oops. Oh, yeah, I got a V and an omega there. I gotta get them in terms of the same thing.
The board was right.
V is equal to omega R, or V over, or omega is V over R. So this is Q omega, wait a second, something's amiss.
Where does the square
Oh,
go?
that's it. Which is Q omega
It really
B
is.
over M. So omega is equal to QB over M. All right, so I know what the angular speed is. It's like it's on a string and you're spinning it around. And I just need to figure out time. Well,
Is this a cake thing?
pardon?
Is this like a cake formula?
Yeah, you could. I mean, there's no angular acceleration. No, sorry, try that one again. Yes, there's no angular acceleration here. It's centripetal acceleration. So I have it traveling basically 75-degree arc. So, let's see, I've got, that's something in radians. I know this angle here, oh, there we go. I know that angle. Try that again. I know that S is equal to R theta. Standard relationship. So theta I know, R, I don't know S and R.
Don't know what it's.
Alright. They're gonna have that it's 1.31 radians.
Okay, so 1.31 radians. So the amount of time it takes, oh, I know omega. Omega is QB over M, but it's also the angle divided by time. So the time would be the angle, 1.31, times the mass divided by QB. There we go.
Oh, we have that. Oh.
And it doesn't, and notice, I didn't tell you how fast it was traveling, it actually does not matter.
So what's the S equals R theta?
Arc length is equal to the radius times the angle in radians.
Yeah.
Okay, so S is R.
Wait, so, I don't understand conceptually how an initial speed wouldn't affect that.
All the speed it's gonna do is change the radius. If it's traveling faster, it's gonna have a bigger arc than if it's
Oh.
traveling more slowly, but still
Okay,
Oh, I get it, because we have the angle, so that decides the arc, thus velocity is irrelevant.
right.
There
Questions?
we go.
How do we get the time is equal to theta M over QB?
We found omega over